My tour guide today couldn't be more experienced. Danny is the co-general manager of worldwide semiconductor manufacturing and started at Intel working in Fab 8 in Jerusalem, back when their state-of-the-art was the Pentium 1. Microprocessor fabrication experts can safely skip ahead a couple of minutes, but for everyone else, let's run through the basics. Every CPU die, every one of these, starts with a sliced up silicon ingot like the one right here. These are astonishingly pure and are exactly 300 millimeters in diameter. If they went any smaller, they'd increase waste around the edges. I mean, look at this. Obviously, this is not going to be a working chip if it's cut off by the edge of the circle. Fun fact, by the way, the reason that they run the non-working edge dies through all of the same fabrication processes is that it actually improves the uniformity of the full chips next to them. Consistency is key in CPU manufacturing because even though we talk about these chips in terms like 14 or 10 nanometer, the components that make up these transistors are much smaller, like on the order of less than a nanometer. And a tiny error or contaminant in any of the hundreds of manufacturing steps means that that die, he no worky. I mean, it's a modern miracle that any of this is possible and is basically unheard of to get an entire 300 millimeter wafer through the fab without a single defective die on it. Before it can be sold, however, it needs to be transformed from melted sand like this into the brains of your PC. Silicon, you see, is neither an insulator nor is it a true conductor. So to create all the little transistors or switches that control current flow through the logic gates and other microstructures on the chip, the wafer needs to undergo many processes. Implantation fires dopant ions into the surface of the silicon to alter its electrical characteristics. So depending on what kinds of ions are implanted, say phosphorus or boron, you might be laying the groundwork for an N-type or a P-type transistor. This determines if the voltage is negative or positive to open the gate. Diffusion furnaces create new combined materials by exposing the wafer to various gases at up to hundreds of degrees Celsius. Lithography is one of the easiest steps to understand conceptually, but also one of the most important. Within a single processor die, there are billions of transistors and literally kilometers of tiny wires. But they're obviously far too small to build them and solder them together by hand. So the wafer gets coated with a material called photoresist, then exposed to UV light through a mask. Anywhere the light passes through the mask, the photoresist will be removed, allowing the exposed portions to be processed. Then it's quite literally rinse and repeat. Nikon, who does a lot more than make cameras by the way, has a great diagram on their site demonstrating this. So one such potential processing step is etching, where the goal is to selectively remove material from the top of the wafer, creating trenches in it. These can be overfilled with copper to create interconnects. Then the excess gets removed by polishing it off using brushes and slurry in a process called chemical mechanical planarization. There are different kinds of etching, but we can talk about that more once we get inside. This is it. Point of no return. Here we go. There's no card or anything. Just yeah, it's very good, high security. Time to learn the procedure. This is great. This is very inclusive. They have child-sized gloves for people like me. This is crazy. So these are not the gloves we wear in the clean room. These are the gloves to put on the stuff that we're going to wear in the clean room that will be contaminated that then we will get rid of after. Wow. Man, I'm looking sharp. Now time for stage 2. Basically, we grab a couple of little foot cover doodads here, and this room is pressurized. And the idea is that these aren't like filtered like the clean room or anything like that. But by having a little bit of pressure in this room, we keep the super stanky air from outside out. So when you walk into here, you feel this gust of air coming out. And then what you're supposed to do is you're supposed to have dirty stuff on this side and then clean stuff on this side. So I gotta put my little booties on. Did I do it right? Yep. Okay, so there's more positive pressure in here blowing that way, right? Yeah. So the idea then, I guess, is the air gets cleaner and cleaner as we go. Okay, what do I do?
You start with the hood.
Yeah. Top to bottom. Yeah. Okay, why do we go top to bottom? So that the dust won't fall off our top onto our bottom?
Better that it will suit into the bunny suits.
Oh, got it. Because that's how the garments overlap. I have a feeling our audio is not going to be our finest ever for this video, ladies and gentlemen. You'll have to bear with us because my microphone is already under 3 layers of fabric now. We're out of the gown room into the fab.
into the fab.
And it's already crazy. Okay, see these like robots on tracks up here? Apparently these are taking the FOUPs, and I checked, that is actually what it's called, FOUP, which is 25 wafers. So that's 25 slices of the original silicon ingot. That FOUP we just saw, that little robot on the track, had hundreds of CPU dies in it, but we don't know how many of them are good because they're actually on their way to sorting, where not only will they determine if they work, but they'll determine how well. So is it a Core i7 or a Core i9? Every guy wants to live. It sounds like a nerdy James Bond film. I love it. Oh my God, this place is a lot bigger than it initially looked. How many square feet is this? 4 football fields.
So the photography is over here. Diffusion is over there.
Diffusion over there.
We go to the diffusion.
And deposition was over there?
Right, and what and etch is on the other side.
Etching.
And plano.
And planing. So we're going to look at all of that, but there's no particular order for these steps because once a FOUP comes in here, you guys can see they're whipping around all over the place. There are hundreds of stages. Each Alder Lake CPU die might go from lithography to planing to deposition, back and forth, hundreds of times. Every silicon wafer comes to diffusion land. And basically what these machines do, they're more like a furnace. And they will take that top layer of silicon on the wafer and they will diffuse it with some kind of other material. I asked for some examples, but other than silicon oxide, they wouldn't really tell me anything. And in fact, they wouldn't even tell me what the first material layer would be for the processors that they're making here now. There you go. We can actually see the robot arm inside that would take the silicon wafers out of the FOUP and position them as needed for the machine. This is the loading area down here that we can see through the window. And then up top is the actual furnace where it reaches hundreds of degrees and then it has gases in there that help them to achieve whatever kind of chemical changes that they're going for on top of the wafer. One thing Intel's been very particular about is don't touch anything because it's more than just, not pressing the wrong button, but actually even just bumping these machines. When you're trying to build something that has structures in it that are on the size order of nanometers, that means that the building blocks of that thing are sub-nanometer in some cases. So you cannot bump one of these machines while it's running. And in fact, they only build their fabs on particularly stable parts of the world where they don't have to worry about excess seismic activity. This is cool. As we were walking through diffusion, we actually got a great opportunity to show you guys the multi-level structure of the fab. So what we're walking on is only one of 4 total layers. Above us are filters, and the air comes from there down to here. Then below us is where they're going to have pumps, chemistry delivery. You can see these punch outs in the floor here. You can actually see there's like a foam vent of some sort going up into the machine that's next to us. And then the air flows from top to bottom. So it goes down to that layer, then it goes down to one more layer where they have water utilities like electricity as well as exhaust. So that air goes back up the side of the building and recirculates. In total, Intel expects anywhere from 0 to 1 particle per, what was the unit of volume? 1 meter cubed. And for context, an operating room could have tens of thousands of particles per meter cubed. So you could conceivably perform surgery in here, assuming you were qualified. I asked about this sign, and apparently it's just to make sure that if people are going through this corridor, they don't accidentally smoke someone coming out of the reticle room. This is one of the most secret areas, even here inside the fab, which is already a secret area, because it contains some of the most expensive materials that they need for lithography. It's also some of the most top secret. Now, under normal circumstances, every one of these stations would be occupied by someone. In fact, the entire factory runs on 4 shifts a day, 24/7, 364 days a year, only shutting down for Yom Kippur. So I didn't ask because I'm afraid to know the answer, but I think it's probably costing Intel a fair amount to have us in here poking around. While they didn't sponsor the video or anything, definitely shout out to Intel for how much it's costing them for us to make this video. On that note, here's something cool. These tools are maybe not as sophisticated as some of the other tools here in the fab. Got your flathead screwdriver, but the process is what's fascinating, because taking a machine like this offline for more than a few minutes at a time, very, very costly. So they handle it kind of like a Formula One pit crew. They've got all their tools, everything's arranged, freaking ready to rock. They go, okay, time, we're shutting it off, we're performing maintenance, go, 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 fire it back up. That's it. Don't worry, I will not hit any buttons. This is the emo button, okay? The machine will get very sad if you press it. This machine right here is doing dry etching right now. So the foops come down off of the track up there, and then while they're waiting, you can see they're actually sitting out, so they sit away from the machine, and while they're being processed, they come up right next to it here, and then you can see there's a robot arm inside, grabbing wafers, whipping them around. It just throws it on here for a span of, I don't know, 5 or 10 seconds. Boom, it's dry etched, it goes back in the foop, and then that whole foop is gonna head off to whatever the next step is for this particular processor. We don't know exactly what it's making, but everything here is Intel 7, so modern CPUs pretty much. Or maybe future CPUs for all I know. Not every dry etching machine is identical, as you guys can imagine. For all the different specialized processes that a wafer goes through, there might be different machinery. So this is another example of a dry etching machine where the wafer actually sits in this chamber in here and does whatever the heck it's doing. Now we're heading back to the lithography area again, which is why the lighting in the fab has changed back to yellow. And the reason for that is they use UV light to expose the wafers. So if they had white light, it could easily contain parts of the spectrum that could accidentally expose the wafer. So they have to use these carefully controlled light sources that will not cause any damage to the wafers as they're ripping around in the foops or going in and out of the machines. Fun fact, each of these machines costs on the order of $30 to $40 million. And it doesn't take a rocket scientist to figure out, or I should say a chip architect, to figure out that when you put this many of them packed this tight into an area the size of 4 football pitches, that's going to cost a pretty penny. And it's because of those costs that they actually have this entire sort of row of cabinets, I guess you could call it, in between the east and west sides of the fab. This entire thing is full of foops that are just waiting to be processed, because the second one of those machines is available, you want to be loading it up with silicon so you can make more processors. Now we're out of lithography again. We're in the east side of the fab, which is also freaking enormous. And the first machines that we're encountering are deposition machines. So what these do is they'll take the wafer and they'll apply some extraordinarily thin layer of something, say for example, metal. Okay, then it comes back into the loop, back up to the rails, and off to the next step. Did I ever say we're going to go see the planers? You did. Now, depending on the stage of wafer processing, because remember, it could go back and forth hundreds of times for a single die, you don't necessarily want the straight edges of a dry etch. You might want this kind of curved shape of a wet etch. Now, the actual exact shape is apparently extremely important and extremely difficult to control, because unlike a dry etch, you can actually hear the sound of the pump. You hear that right now? So there's actually chemicals pumping inside. Another key consideration if you've got such expensive machinery is training. So one of the things that Intel wanted to show us is how they're using augmented reality practically right here in the fab for a variety of purposes. So one is due to COVID-19, obviously some personnel were not able to be here in person for an extended period of time. So remote assist allows someone who is here in person to actually have someone else scribbling on a schematic or explaining it to them while it hovers in front of them. Pretty freaking cool. It's also used as a training resource for maintenance for the machines so that you can kind of learn by doing. And they're actually going to do a practical demo for us. Hey, here's our test guinea pig here. And he gets to look at my mug. That's unfortunate. Oh, that's awesome. So it shows you all the tools you need. So there's a little instructional video for how to do it. Very cool. Hey, look at me. I'm a fab equipment maintenance technician. Unfortunately, the windows on these machines are quite dark, but we did manage to catch one that is being processed right now. So we've got some footage to show you guys. Essentially, after the deposition step, you're going to end up with some inherent unevenness that needs to be polished off. Now, in the past, they might have actually submerged the wafers for polishing, but now it's actually done by a brush that has a slurry on it that Intel said is very proprietary. They wouldn't even give me any hints as to what is in this polishing liquid. But they did tell me that the pressure as well as the motion of it has to be so precise that they could take off as little as a few atoms or molecules at a time. So you can see the wafer moving back and forth on the spinning bottom. Crazy. One thing that's missing is I don't see where that tray that loads all the wafers in is. Where the FOUP is it? Haha, get it? Because it's a FOUP. By the way, something I didn't mention before is that each of the different types of machines actually has a number, but it also has these animals. Because Intel found that, especially in a multi-layer design like Fab 28, in order to make sure that the maintenance crew down below is actually, shutting down the correct machine for maintenance up above, it's much easier to communicate and much easier to remember. Oh, we're working on a giraffe machine or a ladybug machine. Apparently, most of the staff that we saw in there, though, were actually maintenance staff for the machines. And the actual control center or brain of the operation is elsewhere. So we're going to head over there now. This is the remote operational center, which is, you could think of kind of like the brains of the fab that we just saw. So if something goes wrong, it's going to pop up as an error on someone's screen. So it's the job of everyone in this room to optimize the overall throughput of the fab. So instead of having technicians there on the fab floor, moving things around and looking at screens and turning dials, everything is done right here to ensure that they're pumping as many chips out as possible, because once you invest $30 to $40 million in a machine times however many were in there, you want them going as hard as you possibly can, as often as you possibly can. Every shift, they have to do 2 stretching sessions in order to, minimize the risk of RSI, because they're basically sitting at their computers all day, every day, right? But like the friend who only invited you to dinner because he wanted to show off his new car, Intel had a bit of an agenda for inviting us here, and that is to show off the enormous investment that they're making into Fab 38. So everything that we just saw is about to be doubled. This roundabout, see you later in about 2 weeks. That entire construction site out there is going to be state-of-the-art, new generation fabrication technology that will actually be integrated so tightly with the existing fab that you could actually take a wafer from one, utilize equipment in the other, and then send it back if you really needed to, although that's going to be quite a distance for the FOUPs to travel. To give you some idea of how enormous this construction project is, Intel actually built their own concrete production in the corner of the lot over there, which you can see at the very back. Unreal. One of the big reasons Intel is building out fab capacity so aggressively right now is a new concept called IDM 2.0, where basically, instead of only building their own products, they're going to be fabbing products for third-party companies, which I personally, given that we're sitting in the middle of the largest ever global silicon shortage, am pretty excited about. Now, unfortunately, there are a couple of steps in the die creation process that we weren't able to see today. The addition of the bumps that connect the die to the package through electroplating, that doesn't happen here, and quality control. QC starts with an end-of-the-line E-test, which checks the functionality of fake debugging structures and transistors that are specifically meant to be there to ensure that everything went correctly in manufacturing. Then it proceeds to binning, which is the process of sorting the good dies according to their capabilities. Obviously, the best of the best will become Core i9, the next best will be Core i7, and so on and so forth. Other than that, 12th Gen Core, or Alder Lake, is a pretty unique product for Intel, with much of the design and manufacturing done here in Israel. Once the wafer's done, Intel sends it to one of their other facilities for slicing and packaging, and a second validation step called class, where they basically burn in every single chip to ensure that no degradation took place and that the packaging was done properly. This, along with design phase testing that simulates the effects of CPU aging, is where Intel's reputation for manufacturing quality comes from. I mean, think about it. When you're troubleshooting a system that won't boot, the CPU is the last thing you're going to check, because unless you dropped it, it probably works. Packaging, by the way, is going to be getting a lot more complicated over the next few years as multi-die processors like the upcoming Sapphire Rapids start rolling out. And it's expected that the relatively basic packaging facilities of yesteryear are going to be getting a lot more fab-like. I mean, a packaging error on a $10,000 server CPU is a pretty expensive mistake, given that the whole thing needs to be thrown away at that stage if something goes wrong. Maybe that should be the next tour I request. Am I right? Actually, I'm not going to push my luck at the moment. This was a once-in-a-lifetime opportunity, and I'm extremely grateful to Danny and his team, shout out to Karen, by the way, for hosting me, to you guys for coming and sharing it with me, and of course, to my sponsor.
Ting Mobile. Ting Mobile has rates that make it easier to see how much you can save by switching. They have a perfect plan for everybody, no matter what your needs are. Unlimited talk and text for $10. Data plans that start at $15. Then there's their Set 12 plan with 12 gigs of data for $35 and unlimited data for $45. If you like their previous pay-what-you-use plans, T-Mobile's Flex plans charging just $5 per gigabyte are still there. Data can also be shared if you have a family plan, so connect more phones to save more. You'll still get nationwide coverage and award-winning support. In fact, Consumer Reports named T-Mobile their #1 carrier in America. Pretty much any phone will work with T-Mobile, so check them out at linus.ting.com and receive a $25 credit.
If you guys enjoyed this video, maybe check out one of our previous tours. It's been a little while, but they're excellent videos.